All right, so we're on chapter 8 now because we skipped everything else, and this is sequences. So we're going to start with definition. There's only one definition, and the definition is sequence. So what is a sequence? A sequence is an ordered list of numbers. That's a pretty short definition, so you guys should have no problems with that. So let's take a look at how you write a sequence. You guys should have seen this before. So every term in a sequence is denoted by a with a subscript. So the first term in a sequence is denoted by a sub 1. The second term is a sub 2, and then the nth term is a sub n, and then so on and so on. The way we write it is with these, what are these called? Squiggly brackets. I don't know what they're called, but you put it inside those brackets like a set. So if you look at the first one on the right, you have a sub 1, comma a sub 2, and so on and so on. So that's how you write a sequence. They can also write it with a sub n, and a sub n is usually denoted by some sort of formula that tells you how to get a particular term in the sequence. And then they can also specify the index. So the index is basically the subscript. So like a sub 1, the index is 1, and so on and so on. So the index usually starts at 1, and a sequence can have a finite amount of numbers or infinite amount of numbers. Okay, so just to get familiar with the notation, why don't we try these 3 exercises. So here we want to write down the first 5 terms of the following sequences. What class do you learn sequences in, by the way? I don't remember. High school, algebra 2. Okay, so that's all high school. All right, cool. So it's been a long time then. All right, so the first one says n plus 1 over n squared is your formula for the nth term. The index starts at 1 and you have infinite amount of terms, but we're only listing the first 5, so it doesn't matter. So this is equal to bracket. Let me change colors. So this right here is basically a of n. So your first term is when your index is 1, so when n is equal to 1, which means you will get 1 plus 1 over 1 squared. So what would that be? That would be 2 over 1. So the first number in your sequence is 2. And then the next number is when the index is 2, so that's 2 plus 1 over 2 squared, which is 3 over 4. And then you plug in n equals 3, which is 4 over 9. And then, yeah, you guys get the point. So the next one is 5 over 16 and 6 over 25, and so on and so on. Okay, let's do the next one. So here the index starts at 0, which is uncommon, but it can happen in some questions. So when the index is 0, what is your first number? we have -1 to the 0 plus 1 power over 2 to the 0. This is -1 to the first power over 2 to the 0 power. That's -1 over 1. So -1. Yeah, just let me know if I make a mistake. So next index is 1. So we're going to have -1 to the 1 plus 1 over 2 to the first power. So that's -1 squared over 2. So that's 1/2. Okay. What's the next one? So it's -1 to the third over 2 to the second. So that's -1 over 4. I think there's a pattern here, right? What will be the last two terms? I think it's probably +1 over 8, I think. I'm just doing this in my head, so let me know if I make a mistake. -1 over 16. I think those are the last two terms. This is right, right? -16, -1 over 16 is the last term, or the fifth term?
Yeah, it's right.
Okay. So for this one, I just want to notice a few things. So the -1 that's in the numerator, what does that contribute to like the pattern of our sequence? Yes, the sign. So the -1 basically makes the sequence alternate signs as you go from one term to the next, right? So that's something to take note of. Okay, let's do the last sequence. Sometimes the index starts at 0, so unless it states it starts 0, should we assume it starts at 1? Yes. Some questions where they don't give you a starting index, it can also mean that you can just choose what the starting index is, as long as you're consistent with whatever you chose when you're doing the problem. Okay, so this one says the nth term is b of n, where b of n is the nth digit of pi. So, okay. So when n equals 1, that means we're looking at the first digit of pi. What's the first digit of pi? You know, I should probably just list out pi because I don't even know what it is. So it's 3.14. What comes after that? 1, 5, 9, 2, 6, 5, 3. Okay, so as far as this sequence is concerned, the first number in our sequence will be the first digit of pi, which is 3. When the index goes to 2, so we have when n equals 2, that means we're looking at the second digit of pi. So what's the second digit of pi? That would be 1. And then the next digit of pi, and then the next one, and the next one. Okay, so this is our sequence. Okay, so hopefully you guys are remembering how to use sequence notation. You guys all good? All right.
I have a question for the bracket. Do we have to incorporate a bracket like for like the first and second question, or do we just leave dots?
Yeah, I mean, it doesn't really matter. I guess you could just to like be more formal. But since we're just listing the first 5 terms, it doesn't really matter. Because the bracket just means like you finished writing all of it, which you didn't, but it's okay.
All right, got it. Thanks.
Okay, back to the PowerPoint. Is B always digits of pi, or are you just calling it that? it's just for this particular question, that's how they define this, the sequence. All right, so next slide says you can actually graph a sequence. So if you look at the first sequence we looked at, which was n+1/n², our numbers were 2, 3/4, 4/9, 5/16, and 6/25, right? You can sort of think of it as coordinate points. So the first number was 2. You can sort of think of it as a coordinate point 1, 2. And then the second number was 3/4. So that's 2, 3/4. So if you have these 5 points, you can graph it on the XY axis like so. And then you can see the shape of your graph for your sequence. So it's just a bunch of dots, okay? Unlike a function, which is usually like a curve, the graph of sequence is dots. All right. So much like functions, we can also take the limit of a sequence. So for example, this limit we looked at earlier, n+1/n², the limit here goes to 0. So why does it go to 0? Well, there's many ways of reaching that conclusion, but the easiest way would just be to look at a graph. So if you look at the dots we plotted, you can see how as we go further and further to the right, then the dots get closer and closer to 0. Yeah, and you can also see like when you plug in a really, really high index, you'll get a really small number. So you can also take the limit. On the right, it says, much like functions, if the limit of a sequence goes to some sort of infinity or does not exist, then we can say the limit of the sequence diverges. Yeah, so that's the same thing as functions. All right, let's see. Okay, so there are specific sequences that have a special form. And here we have 2 of those. So we have an arithmetic sequence and a geometric sequence. You guys have heard of those, right? Say yes if you have heard of it. Okay, so someone who has heard of it, can you just explain briefly like what makes something an arithmetic sequence and what makes something a geometric sequence?
So basically the arithmetic sequence is adding the same value over and over again, but geometric sequence is multiplying a value over and over again.
Yes, thank you. All right, so arithmetic has a rate, geometry is like exponential. Yeah, you can think of it like that. Yeah, that also works. Let's see if we can come up with the general formula for those 2 sequences on the right. So spoiler alerts, I stole these 2 examples from your homework. In case you guys forgot, I'm just going to go through what each symbol means in these formulas. So A of n is the general term. A1 is the first term. N, that's your index. And D is what you call the common difference of an arithmetic sequence, which is basically the number you have to, it's the difference between each term, basically. So if you look to the right here, we have the sequence 1, 3, 5, 7, 9. What would be the common difference here? 2. Yeah. So to get the common difference, you just have to take one term and then subtract it by the previous term, which gives you 2. So here we know that A of n is equal to the first term, which is, in our case, is 1, plus n minus 1 times our common difference of 2. So this gives us an expression for the nth term. So if you simplify it, you will get 1 plus 2n minus 2. So you get 2n minus 1, okay? So this will tell you what the nth term is. So if you want to know like the 100th term, you can just plug in 100 here and that'll tell you what the 100th term is. Okay. Let's do the other one. So here, you guys probably can figure it out, but this is a geometric sequence. And in the formula for geometric sequence, we have this variable r, which is called the common ratio, which is the number you have to multiply by to get from one term to the next. So can someone see what the common ratio is in this geometric sequence?
-2/3.
Yes. So if you guys observe, to go from one number to the next, you have to multiply by -2/3. So if you wanted to write the general term, this is a of n is equal to the first term times the common ratio to the n minus 1 power, okay? So this is your general formula. Any questions so far? Refresher of high school material. All right, let's continue. So when we learned about limits, there was a lot of properties that we learned, most of it of which we sort of just ignored because we didn't really think much about it. Like when you have a limit of, say, x squared plus 3x, you just take the limit of each one separately, right? And you just add it together. So you can apply all those properties to sequences. So the first one says you can add sequences. If you have a constant, you can pull it out. If you have a product, you can take the product of both sequences and then do it like that. Yeah, this is whatever. So here we have a important theorem for sequences that we should take a closer look at. So theorem says if you have a sequence, a sub n, and then you have a function such that each y value of the function is equivalent to the corresponding nth term of the sequence, then both the function and the sequence will have the same limit. So let me see what they wrote here. In other words, to evaluate the limit of a sequence, we can evaluate an otherwise equivalent function instead. So this is useful because we can use techniques for finding limits to find the limits of sequences. Here we have an example. So the function we looked at earlier was n plus 1 over n squared. Well, that was a sequence we looked at earlier. And that sequence, we figured out that it went to 0 as a limit. But if you look at the equivalent function, which is on the left side, that would be x plus 1 over x squared. And that function actually goes to 0 as well as x goes to infinity. So you can see how instead of finding the limit of a sequence, we can just find a limit of the function instead and then just say that's the answer. Okay. Moving on. Over here, we have another theorem that says if the limit of an absolute value of a sequence is 0, then the limit of the original sequence is also 0. So let me see if I could draw that for you guys. Okay, so let's say we had a sequence that alternates signs, right? So first it's positive, then it's negative, then it's positive, then it's negative, then it's positive, then it's negative, then positive, then negative, then positive, then negative, and so on, right? So then its graph will look something like this. And then based on the way I drew this graph, can you see what the limit is as I go further and further to the right? Yeah, so the way I drew it, you can see that the limit as, okay, let's call this the n axis. So limit as n goes to infinity would equal 0. But if you were to take the absolute value of this graph, that would make it look something like this. So everything that was underneath the y-axis would just get flipped to over the y-axis. So it was positive and then negative, but then the negative one would get flipped to the other side. So then it would look like this. So it would look in a way where everything was above the y-axis. And then based off of this picture, can you see where the limit is going? So you guys can still you can still see that it's going to 0, right? So that's just an illustration as to what this theorem is saying. So if you have the absolute value of a limit, which is this one right here, if that goes to 0, then the original one will also go to 0. So the original one was this one, okay? All right, so that's an illustration of that theorem. Moving on. Okay, so here are some typical questions that you'll see when you're doing questions in this chapter. So you'll find these in your homework, and you'll probably find similar questions on the exam as well. So let's try to do these. Do you guys want some time to do it by yourselves, or do you guys just want to do it together? Can you do it together? Okay, yeah, let's do it together. All right, so the first sequence is 3n squared minus 1 divided by 10n plus 5n squared. Okay. So just so we know what we're talking about, can someone tell me maybe like the first, I don't know, 2 numbers in this sequence? What's the first number? So it's 3.
It's 11 over 40.
11 over 40. Okay, yeah, let me just show the work. Sure, all right. So 11 over 40 is the first number in the sequence. And then I guess we'll just say the second number and call it there. So what's the second number? So that would be 3 and 3 squared minus 1. That's 9 times 3 is 26 or 75. Okay. All right. So, okay, so we know what this sequence is doing. Now the question is to find out whether it converges or diverges. So from listing two numbers, I don't know if it's obvious what it does. So we can't really reach a conclusion yet. So we have to use actual like mathematical stuff. So one thing we could do is just to convert it into a function. So instead of thinking about it as a sequence, consider this. Consider 3x squared minus 1 over 10x plus 5x squared. And then let's take the limit as x goes to infinity, right? We can do this because of that first theorem that said you can just evaluate an equivalent function. So do you guys remember how to take the limit of this?
Yes.
Yes, someone knows how to take the limit, so we can move on now, right? To question number 2. All right, can you explain how we can do that? L'Hospital's rule, divide by highest power. Yeah, so divide by highest power would probably be the simplest option. You can use L'Hopital's, but you don't really need to. So if we divide everything by the highest power, we will have limits as x approaches infinity of, so dividing everything by x squared, we're going to get 3 minus 1 over x squared over 10 over x plus 5, right? So now as x goes to infinity, anything that has x in the denominator will go to 0. So this goes to 0. This goes to 0. So this leaves you with 3 over 5. So because the limit of the function goes to 3 over 5, we can also conclude that the limit of this sequence also goes to 3 over 5. Okay. So this converges to 3 over 5. Okay. And then if you want to verify, you can always just plug in like a really, really big number for n into a calculator, and it should give you a number really close to 3 over 5. Okay. All right. So that's that. Let's look at the next one. Okay, so we have e to the 2n over n. Any ideas here? L'Hopital. Maybe. If we were to list out the numbers in the sequence, it would be e squared over 1, and then e to the 4th over 2, and then e to the 6th over 3, e to the 8th over 4. Okay, so those are the numbers in the sequence, and so on and so on. Just from writing it out, can you guys see what might be the answer? Yeah, it does seem like it's going to infinity, right? Because the numerator is growing a lot faster than the denominator. So we probably expect our answer to be infinity, but we have to actually like go through with it just to prove it. So let's use the theorems we learned. So you said L'Hopital's rule. You can use L'Hopital's rule, but just remember that L'Hopital's rule is, what did you lie about? So L'Hopital's rule is use for evaluate limit on functions. This is not a function, this is a sequence. So what we do is we just change it to a function. So consider limit as x approaches infinity of e to the 2x over x. So here we are, we have a function now. That means we can use L'Hopital's rule because we have a function. So when you use L'Hopital's rule, what do you get? So the derivative of e to the 2x is 2e to the 2x. And then the derivative of x is 1, right? Okay, now we can evaluate the limit of this function, which gives you infinity. So just like we predicted, the limit of the function goes to infinity, which means the limit of the sequence also goes to infinity. So this diverges. Okay. So you guys can see that the index doesn't really play a role in how we find a convergence and a divergence. All right. How are you guys feeling so far about sequences? Good. Great. I'm happy to hear that. All right. Let's do this one. So here we have -1 to the nth power divided by n. And then just so we can get a feel for how this works, let's list out some terms. So when n equals 1, we have -1 to the first power over -1. That's just 1, right? And then when n equals 2, we have 1/2. Is that right?
Wouldn't the first term be -1? -1 to
Oh,
the
yeah,
power.
because, yeah. Okay, so -1 and then positive 1/2. And then, so we established before that the -1 to a power sort of alternates your signs, right? So the next one's probably negative something. So it's -1/3. Okay. And then positive 1/4, right? Okay, and so on and so on. So based off of this pattern, do you guys think you can predict what the answer might be?
No.
No?
Wouldn't it just be like infinity?
I honestly don't think it's going to go to infinity because the numbers are getting smaller. So probably not infinity. People are saying 0. Yeah, I think it's probably going towards 0 because the denominator is just, so the numerator is staying the same, but the denominator is getting bigger. So it's probably going to 0. But how can we show that? So, So there is a theorem we can use here. Do you guys think you might know which theorem we can use? How many theorems did I give you guys? Oh, I only gave you 2 theorems.
Would you be able to use the second theorem, the one with absolute value?
Yeah. Okay, so let's use that one. So instead of considering this sequence, we can consider the absolute value of it. Consider the absolute value of -1 to the nth power over n. So if you were to take the absolute value of this particular sequence, the -1 to the nth power in the numerator, all that does is it alternates the signs, right? It makes it positive or negative. If you were to take the absolute value of everything, that basically just like it cancels out anything that the numerator does. So it just becomes 1 over n, right? And then this particular sequence here, 1 over n, that one is pretty obvious as to where it goes, right? Where does this sequence go? So this right here, 1 over n is the sequence 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on and so on. So where does this one go?
0.
Yeah, so this one goes to 0. So because the absolute value one goes to 0, we can conclude that the original one also goes to 0. So converges to 0. Okay, so that's that. And last one. So here is the last sequence. Is there a name for this formula? Which one? The one with the absolute value? I don't think so. You can just call it theorem 2. Yeah, I don't think there's a name for it. All right, last sequence. So -1 to the n. Who can tell me what are the numbers in this sequence? One. Yep, so the first number is 1 because that's -1 to the 0 power. And then how does it continue? -1. And then it just keeps going, right? 1, -1, 1, -1. All right. So based off of that, do you guys think you have an answer for whether this converges or diverges? If we were to draw a graph for this sequence, it will look like this. So you have 1, -1, and then 1, -1, then 1, -1. So it looks like that. Is it converting towards any number, or is it just doing something else? Diverges. Why do you say it diverges? Because it's kind of like cosine. I see. oscillating. Yeah, that's basically it. So this diverges. And the reasoning is pretty much the same reason why we call trig functions divergent. So let me write divergent. So the values of this sequence just oscillate between 1 and -1, right? So if you were to think about what value it will get closer to as you reach the right side of the graph, it's not going to really reach one particular value. It's going to be 1 or -1, which is a similar situation to sine and cosine, right? That also oscillates between 1 and -1. And we know those are divergent. So a sequence that behaves the same way is also going to be divergent. Okay, so we can write divergent. And yeah, that's pretty much it. All right. That's all the examples we have for today. So does anyone have any questions?
Professor, like if we didn't have the graph or like most of the values in the sequence, right? And we were to find like the limit of a function from like if we saw like from looking at the value of that limit, can we conclude if something's divergent or not?
Can you say that one more time? You said if you're just looking at the value of the limit?
Yeah, so like without looking at the elements in the sequence, if we just looked at the value of the limit, like for example, the limit equals -1
Mhm.
or something like that, you know, like is there any value that indicates that it's divergent, like a unimaginary number or something that doesn't exist?
Yeah, so for divergent sequences, we said that the limit will be either infinity or -infinity or does not exist.
Okay. Oh, I missed that. Okay, my bad.
Yeah, so for this one, it would be does not exist, which is why it's divergent.
All right, thank you.
Mhm. And the second one was infinity. That one was divergence.
Thank you, Professor.
Mhm. Any other questions?
No, that'll be it.
Yeah, I just meant like for everyone else. Okay, well, if there are no questions, so that is the end of 8.1. So on your free time, do try homework 8.1 on Lumen. And next time we will start 8.2, which is series. Okay, so that's it for today. Have a good night, and I'll see you guys Thursday.